Okay. Hi all, and thank you for attending this seminar, and also many thanks for inviting me here at this seminar series. Today I'd like to talk about two things, actually, as you can see, reverse annealing and counterdiabatic driving. And in particular, I'm going to show you how you can combine these two techniques to improve the performance of reverse annealing at short annealing times and basically define what I call counterdiabatic reverse annealing. So if you're interested in the technical details, you can find them in this reference here. Today I will make a broad introduction about the subject and let's see. So, given the audience of this talk, I figured that I don't really have to do my usual introduction about quantum annealing because I assume you are already quite familiar with the subject. So I'll be very quick about this point. And I just want to remind you all what the general algorithm entails in quantum annealing. You want to find the ground state of this Hamiltonian, so you start by preparing your state in the ground state of the transverse field Hamiltonian. You then evolve it in time using this time-dependent Hamiltonian here with these time-dependent functions. At the end, you measure a certain classical string, and this will be your trial solution. So the trial solution to your optimization problem. In order to be sure that this is indeed the true ground state of this problem, you have to repeat this experiment many times. And this is somehow a problem because every time you restart your algorithm, in order to use the adiabatic theorem, you have to prepare the system in the ground state of the initial Hamiltonian. So for example, if this bit string was already quite close to the target solution, you are completely disregarding this piece of information and you are restarting from scratch every time. So reverse annealing was proposed as a way to include this kind of information about this classical bit string in the starting state of the new procedure. And in order to do that, you have to modify in some ways this Hamiltonian because the transverse field Hamiltonian doesn't have classical bit strings as their eigenstates. And so if you want to use techniques based on adiabatic evolutions, you need to have a way to have an initial Hamiltonian that can have classical bit strings as their eigenstates. So the simplest thing that you can do, and it's actually also implemented in the wave devices, is you can tune the annealing schedules. The annealing schedules are controlled by this external parameter S of t, which is typically a linear ramp from 0 to 1, while the annealing time goes from 0 to the total annealing time. And so when your control parameter looks like this, the resulting annealing schedules are something like this. So the strength of the transverse field goes down in time, whereas the strength of the problem Hamiltonian increases. So if you change the shape of this control field, you can also change the shape of the annealing schedules. So for example, instead of starting from s equals to 0, you can start from s equals to 1. In this way, you see that the Hamiltonian at t equals 0 is only contains the problem Hamiltonian term because the strength of the transverse field is 0. So as dynamics progresses, you decrease the value of this control parameter up to this inversion point, and then the dynamics resumes back as usual towards s equals 1. And if you plot the resulting annealing schedules, you see that there is this non-monotonic behavior of the strength of the problem Hamiltonian and of the strength of quantum fluctuations, and this is the footprint of reverse annealing. So you have a classical Hamiltonian at the beginning and at the end of the evolution, and your quantum fluctuations are non-monotonic. So with this advanced schedules, you can reformulate your algorithm in this way. You start from a classical bit string that this time is typically an excited eigenstate of the problem Hamiltonian that you want to solve. You evolve in reverse up to the inversion point. You resume your usual evolution towards s equals to 1. You measure a different bit string and you check if the energy of this bit string is lower than the energy of the state you started from. You restart your algorithm from this new bit string. Otherwise, you disregard this result and restart your algorithm from the bit string you started from in the first place. And you can iterate this process, and this is why this is known as iterated reverse annealing. So why does iterated reverse annealing work? Of course, as you can imagine, since this is typically an excited eigenstate of the Hamiltonian at t equals 0, iterated reverse annealing cannot be based on the adiabatic theorem, because if you initialize the state in an excited eigenstate and your dynamics are adiabatic, the system will be found in the same eigenstate at the end of the evolution. So it means that iterated reverse annealing must involve somehow some diabatic transitions connecting the initial state to the ground state that you want to realize. And for example, in this numerical study that we performed a while ago together with Daniel Idar and Professor Nishimori, we studied the ferromagnetic p-spin model, which is a usual model often used as a benchmark for quantum annealing that has a ferromagnetic ground state. And so depending on the magnetization of the initial state, that is, depending on how far in energy the initial state is compared to the target ferromagnetic solution, and depending on the value of the inversion time for a given annealing time, you can either improve the overlap with the target ground state or not, depending on the value of the magnetization. If your magnetization is too far away from the correct one, which is +1, basically, you see that there is no chance that diabatic transitions will lead you to the correct ground state. So in this sense, it means that iterated reverse annealing, it's a little bit disappointing, meaning that it is not backed up by the adiabatic theorem as opposed as standard quantum annealing, where in a sense there is guarantee of success. You know, even though the minimum gap may close exponentially with the system size, as typically happens in NP-hard optimization problems, you know that if your annealing time is sufficiently long, even though exponentially long, there is guarantee that the algorithm will find a solution. Instead, iterated reverse annealing is mostly a heuristic optimization protocol that relies on two things. One is diabatic transitions, but the most important thing is thermal relaxation, because as we shown in this paper here, if you also consider the fact that these quantum devices are interacting with a low temperature environment, then you see that reverse annealing can be useful, because the low temperature environment can help cool down the system and remove excessive excitations, driving the system towards its ground state. And this is the reason why reverse annealing is actually useful in real devices. But in any case, this is not an adiabatic protocol. And given the title of my talk, which speaks about counterdiabatic reverse annealing, it is evident that you cannot apply counterdiabatic driving to iterated reverse annealing in this form here. But lucky for us, a few years later, there was another proposal of a reverse annealing protocol that is instead based on the adiabatic theorem, and it is known as adiabatic reverse annealing. It was proposed by Professor Nishimori and collaborators, and it looks like this. So as before, you want to initialize your state as a classical bit string, but this time you want this classical string to be the ground state of the Hamiltonian at t equals 0. So in order to do that, you have to include additional terms in the Hamiltonian that can enforce this starting classical condition. So you need an extra control field, this parameter lambda, and you want to engineer this Hamiltonian so that psi is the ground state at t equals 0, where both these parameters are equal to 0. So basically you follow the same algorithm as iterated reverse annealing, meaning you evolve with this Hamiltonian, you measure a different bit string, you check the energy. If the energy is lower than the one you started from, you restart your algorithm from the new bit string with a new Hamiltonian engineered so that the new bit string is the ground state. And what does this Hamiltonian looks like? It's actually very simple. You just have to include this term, which is a local Hamiltonian, where you have these spinning fields that determine whether a spin is aligned in the positive or negative direction in the initial state. And as you can see, the remaining part of the Hamiltonian is quite similar to your standard quantum annealing Hamiltonian. The only difference is the fact that the transverse field Hamiltonian has this additional term here. So the coefficient of the transverse field vanishes both at t equals 0 and at the final annealing time. And so it means that this coefficient must be a non-monotonic function of time. And this is the footprint of reverse annealing. This is why this is called adiabatic reverse annealing, even though it's just a regular adiabatic protocol. And what's the interest towards this kind of reverse annealing? Well, the interest comes from the fact that it has been proven analytically that adiabatic reverse annealing can actually give you an exponential speed up compared to quantum annealing in some cases. And once again, the playground is given by the ferromagnetic p-spin model, in particular already with p equals to 3. The p-spin model is described by this problem Hamiltonian, where you see that you have these three-body interactions between qubits. And when you do quantum annealing with this Hamiltonian as your problem Hamiltonian, you know that quantum annealing encounters a first-order quantum phase transition where the minimum spectral gap will close exponentially as a function of the system size. And so the annealing time required to achieve the adiabatic regime will diverge exponentially as well. However, in adiabatic reverse annealing, if you consider an initial state with a fraction of spins that are already aligned in the correct direction that is above a certain threshold, you can avoid this first order phase transition. The scenario is depicted in this phase diagram here as a function of the two control parameters S and lambda. By the way, lambda equals 1 corresponds to your usual quantum annealing, where you don't have this term and you just have these two terms in the Hamiltonian. So at lambda equals to 1, you see that no matter how you ramp S from 0 to 1, you will always encounter this first order critical point here. However, you see that when the fraction of spins that are already up aligned is above a certain threshold, that in this case is around 0.74, these first order critical lines are split in the middle of the phase diagram. And so you can engineer an annealing schedule that doesn't cross any first order quantum phase transition. Actually, you will only encounter a second order phase transition where the closing of the gap is polynomial with the system size. And so the annealing time that you need will grow polynomially as well. And this results in the exponential advantage that I was mentioning before. Actually, it turns out that this exponential advantage is very sensitive to noise. This is another work that we did with Daniel Lidar. In the unitary limit, you can see, for example, this is a usual metric of success in quantum annealing, that is the time to solution. You see that when you compare adiabatic reverse annealing, that are these three curves, to quantum annealing in the unitary case, which is here, you see that you only have an advantage when C is above the threshold, and you see that you get a lower time to solution compared to standard quantum annealing. But as soon as you switch on dissipation, this is collective dephasing, so you're considering here a system in interaction with a thermal environment via a collective spin operator. As you can see here, these curves flatten out and you lose any advantage that you had in the unitary limit. And also, since adiabatic reverse annealing is now based on an adiabatic protocol, at short times, there is a problem because, of course, you are in the quench limit. And so the adiabatic theorem does not apply and there is no guarantee of success. And also, as you can see here, the red line is, again, quantum annealing. If the fraction of spins is too far from 1, you see that the time to solution in the case of ARA will be even larger than the time to solution of standard quantum annealing. So at this point, we started wondering whether was it possible to improve the performance of adiabatic reverse annealing in this short time regime, keeping aside this dissipation problem that we'll likely address in a future work. So concerning the first part, we know that in standard quantum annealing, a way to improve the performance of the quantum algorithm at short times is by using shortcuts to adiabaticity. And in particular here, I will be focusing on counterdiabatic driving. So the idea is as follows. When you have a time-dependent Hamiltonian, you can instantaneously diagonalize it, and you can write down your Schrödinger equation in the moving frame in which the Hamiltonian is diagonal at every time. If you do that, you realize that the generator of the dynamical evolution is given by two terms. One that is the diagonal Hamiltonian, so it cannot induce non-adiabatic transitions, and another one that is instead responsible for diabatic transitions and will vanish in the adiabatic limit. So at this point, from this observation, you can do some sort of reverse engineering of the Hamiltonian in the sense that you can redefine it to include the opposite of this term here, so that when you go to the moving frame, these two terms cancel out, and you will get a diagonal Hamiltonian that cannot induce transitions between energy eigenstates, no matter how fast your dynamics are. And this operator here is known as counterdiabatic driving operator and is shown here in the slide. It can be computed analytically, but the problem is that even though you have this analytical expression, you will never be able to use it in experiments unless in very specific selected cases, due to the fact that this is a non-local operator. As you can see, it is expanded in terms of these projectors of computed from energy eigenstates. You need to know the spectrum of the Hamiltonian if you want to compute it, which is, of course, some information you don't normally have. And it is ill-defined around quantum critical points where these denominators can go to infinity, can go to zero, and so the norm of C of the counterdiabatic operator can go to infinity. So for all these reasons, in this paper here, Seltz-Polkovnikov proposed a different strategy to build approximate counterdiabatic operators that work well for many-body quantum systems and which do not suffer from these limitations here. The key point is to notice that the counterdiabatic operator satisfies a certain operator equation, and that the solution to this equation is also the minimum of this functional here that can be computed in the computational basis without requiring diagonalization of the original Hamiltonian. So at this point, you can just make an ansatz on the form of this operator A, and you can minimize this functional to obtain the best possible approximation of the counterdiabatic operator given your constraints, for example, locality or engineerability in the device. So actually, there is an analytical result that tells you that the counterdiabatic operator has to be expanded as to be a linear combination of nested commutators between the Hamiltonian and its time derivative. So in the limit of infinite k, this will be the exact counterdiabatic driving operator. So of course, one thing you can do is you can truncate this series up to a certain k and just use this as your kth order ansatz of the counterdiabatic operator. You can optimize these coefficients by solving these equations, and you can use this one to assist the adiabatic passage across small gaps in quantum annealing or in adiabatic reverse annealing. So for example, in this paper here, we studied the effect of this approximate counterdiabatic driving on the p-spin model. Here I'm showing the fidelity with the ground state as a function of the system size. This is regular quantum annealing. And as you can see, here you see that the scaling of the fidelity as a function of the system size decays exponentially as a function of n. But if you start including corrections that you obtain from this expansion here, you can drastically improve the scaling. I mean, the scaling itself remains exponential, but the prefactor becomes much smaller. And in the noise intermediate scale era, where every quantum device only runs at a finite quantum volume, all kinds of improvements are of course welcome. So even this very nice prefactor improvement is a nice result to have. And so given the fact that this approach works very well to improve quantum annealing, can we apply it also to adiabatic reverse annealing to extend its applicability also to the short time domain? Of course, we cannot apply it to iterated reverse annealing, but we can apply it to ARA. And in particular, you start from the ARA Hamiltonian, you include this kth order approximation of the counterdiabatic driving operator, and you obtain counterdiabatic reverse annealing of order K. One word here about how we would like to keep this K as small as possible. When you start to compute nested commutators between Pauli strings that appear in the Hamiltonian and its time derivative, the resulting operator becomes less and less local the larger is K. Of course, in the case of the p-spin model, the problem Hamiltonian is already non-local. So this discussion doesn't really apply for this specific system. But if you change the problem Hamiltonian, you consider a local problem Hamiltonian, for example, you want to keep this K small enough so that this approximate counterdiabatic operator will be a local operator as well. And so, for example, what you can do here for the p-spin model, you can fix the fraction of spins C, and you can see what happens to the performance. So for example, to the fidelity as a function of the system size for several values of C. And as you can see here, we get very similar features to standard quantum annealing. The fidelity drops exponentially as a function of the system size in the unassisted protocol, which is the red line here. But when you start correcting adiabatic reverse annealing by counterdiabatic driving, you see that there is this large prefactor improvement compared to the unassisted case. And also we notice another thing that is quite interesting, and that is the fact that contrary to what happens in quantum annealing, where if you keep increasing the order of the expansion, the performance gets better and better, in adiabatic reverse annealing, it almost looks like most of the performance gain is given by the first order in nested commutators, whereas the second and third order are just very small corrections compared to the first order. And this is true both for C0.7 and C0.9. You see that also for C0.9, the features are almost the same. There is this exponential decay, but there is this improvement in counterdiabatic reverse annealing. And also, here we already start to notice something interesting, and that is the fact that when C is equal to 0.9, we should be able to see the effect of the fact that here we are not encountering a first order phase transition, but only a second order one. But instead, apart from a difference in scale on the vertical axis, we see no difference in scaling of the fidelity as a function of the system size. So in the quench limit, neither in the unassisted protocol nor in the counterdiabatically driven protocol. So in the quench limit, we see that actually the scaling of the gap with the system size does not seem to be an important factor for the performance of counterdiabatic reverse annealing or adiabatic reverse annealing. And this is also confirmed by studying another metric, that is the energy cost of counterdiabatic driving, because of course, if you want to assist the adiabatic passage across small gaps, you need to pay an energy cost, and the energy cost is of course due to the fact that you are adding this extra operator in your Hamiltonian. So a way to compute this energy cost is by looking at the norm of this approximate counterdiabatic operator. This is the instantaneous cost, but you can also compute this integral here that gives you the average cost throughout the protocol. And this V is just a compact way of indicating the two parameters this Hamiltonian depends on. And theta here is just a dimensionless time rescaled by the total annealing time. So as you can see, in this particular case of 50 spins, both for 0.7 and 0.9, we see that most of the cost is due to the first order in nested commutators. The other two curves are just small corrections. And you see that apart from a difference in the vertical scale, there isn't much of a difference between these two cases in this case as well. And also when you compute the total cost or the average cost of the entire protocol, you see that no matter the order of the phase transition, in this quench limit, you will see that the scaling of the cost with the system size will remain the same regardless of the order of the phase transition. And this can be understood because in this quench limit, we are not really seeing the fine details of the spectrum. We are just seeing an overall spectrum. And this is something that we have addressed more specifically in the paper, but in the case of ARA, not specifically for CRA. So if you're interested about this point, you can have a look at the reference. But here, to convince you further that the gap scaling does not affect the performance of CRA, that is only determined by how far the state is from the target ferromagnetic solution, let me just focus on the case of C0.8. Because from this phase diagram, you should see that for C0.8 is quite a borderline case, because you see that the first order critical line is split in the middle, but if you consider a linear annealing schedule like this schedule will still cross the first order phase transition. And so you should see an exponential scaling of the gap with the system size. Whereas if you consider a different annealing path, for example, this one that corresponds to a value of Q equal to 1/2, you should see a second order phase transition and thus a different performance of ARA and CRA possibly if the gap was an important factor for these protocols in this regime. And by the way, of course, this phase diagram is only valid in the thermodynamic limits. So you may object that it is not guaranteed that this will apply also to finite size systems. And this is why we did this finite size analysis here. So basically we derived this phase diagram by plotting the gap as a function, the minimum gap, of course, as a function of these two parameters. And as you can see already from n equal to 30, you start to see that the linear protocol will cross a region where this line here is brighter compared to this region here. The brighter the line, the smaller the gap. So it means that even at finite size, we should see some effect due to the different scaling of the gap with the system size. But instead, what we see is that the ground state probability scales basically the same along the two trajectories, both for Q equals to 1, which is the linear schedule, and Q equal to 1/2, which is the square root schedule. You see basically these two figures, these two plots look identical apart from a very negligible shift between the two cases. That is due to the fact that in this case, gaps are indeed slightly larger, but I mean, there is no difference in scaling in this line. Finally, what I want to show you is a comparison with quantum annealing, because of course, the main motivation of the work was to see if we could improve the performance of ARA at short times, making it competitive with quantum annealing. So as you can see, when the fraction C is 0.7, ARA is drastically outperformed by quantum annealing. And the same is true for the counterdiabatically driven protocols, but you see that the performance gap between these two protocols becomes much smaller compared to the unassisted case. Vice versa, when C is very close to 1, both ARA and CRA outperform quantum annealing, as you can see from this plot, which is, of course, something expected. But in the middle, there is something very interesting, and that is the fact that even though ARA performs worse than quantum annealing, the assisted protocols have similar performances. And this suggests suggests that there is a non-trivial interplay between counterdiabatic driving, reverse quantum annealing, and quantum annealing, because counterdiabatic driving is affecting reverse annealing differently than it is affecting standard quantum annealing. And this is probably due to the fact that we have an extra local term in the Hamiltonian of adiabatic reverse annealing. So probably a local approximation of the counterdiabatic driving operator can help you more if you're using ARA compared to quantum annealing. But of course, this is just one very specific model, and this effect has to be studied also for other models to see if this is a general result. So these are my conclusions. This is a summary of what we did. We applied counterdiabatic driving to adiabatic reverse annealing, and in particular, we applied these low-order nested commutators, and we saw that actually just the first order into nested commutators can be of use to improve the performance of ARA, and this is a very welcome result, because it means that you can keep the locality of your approximate counterdiabatic operator low, and so possibly you can think of including it into your quantum protocols on quantum devices. Also, I've shown some features of this counterdiabatic driving, in particular the scaling of the cost of counterdiabatic driving that does not depend on C, and I've shown that there is a non-trivial interplay with quantum annealing. Now, the only thing that is left to do is to assess the problem of dissipation, and we can do it in two different ways. The first thing you can do is you can try and just add dissipation on the top of what I told you today. So you start from the optimized counterdiabatic operators using the usual closed system version of the variational approach to counterdiabatic driving, and you see what the effect of dissipation is and compare with quantum annealing. Or there are some open system extensions to the variational approach to counterdiabatic driving, with which you can optimize your counterdiabatic operator, already taking into account the effect of dissipation. And so in this way, you may be able to build even a more robust protocol than the one that you would get by applying dissipation on the top. But of course, this is still open research. With this, I will stop. Thank you for your attention, and I'm open for questions.
Great, thank you very much, Gianluca. A round of applause on behalf of the audience. And as Gianluca says, we're now open for questions. So if you have a question, please raise your hand or just unmute and shout out. Maybe I could start with a question. Can you go back to page 9 of your slides, please? Make sure I've understood here. Okay, so in the lower left corner, this is the...
Yeah, this is a phase diagram that you can derive using a mean field approximation that works very well for this model. But of course, this is just valid in the thermodynamic limit. So if we do finite size calculations, we are not sure if we are able to see the effect of the different scaling of the gap with the system size already for these small sizes. I mean, 50 is not really the thermodynamic limit, but apparently if we do some,
question is as follows. So there's some, looking at the thermodynamic case here from the Nishimori paper, there's a critical value of C, which is your fraction of spins that start in the correct state when you begin your reverse anneal.
Yes.
Value, which is maybe 0.7 something, at which there is a region of this S lambda plane where there is no first order phase transition.
Yeah.
And I guess my question is whether that critical value of C changes when you're doing your counterdiabatic reverse annealing. So either in the thermodynamic limit or whether it's meaningful or not in these finite size measurements.
Okay. From what I understand about counterdiabatic driving, this counterdiabatic driving idea is useful to derive, I mean, this counterdiabatic driving operator does change the dynamical generator of your quantum evolution, but the spectrum you will have to refer to is still the spectrum of the unassisted Hamiltonian. So the counterdiabatic driving operator will suppress diabatic transition and stuff between the eigenstates of the unassisted Hamiltonian. So I think you should still refer to the phase diagram of the unassisted Hamiltonian without considering also the counterdiabatic driving operator, because this is just a tool to help you drive the eigenstates of H naught.
So I hear what you're saying, and I think I believe you. Can I just clarify, therefore, in your finite size results in the purple and orange colors here, that is just from diagonalization of the Hamiltonian without the counterdiabatic?
Yes, exactly.
Okay,
yeah.
Fine. Good, interesting.
Can I ask a question?
Please go ahead. Yes.
Yeah, hello. Thank you for a very nice talk. So this p-spin ferromagnetic model, this is a result in particular for that model, I presume, right?
Exactly.
So what happens if you have a spin glass or some cubo kind of Hamiltonian? What of your message goes through and what does not?
I mean, you can always define this kind of protocol because, for example, this classical bit string can be the outcome of a previous optimization routine. So even if you have a Kubo problem, you may have used some heuristic to derive an approximation of the solution to that optimization problem, but maybe you want to refine this approximation. And so you can use this kind of protocol anyways, because you just have to select the spinning fields to enforce.
No, I understand.
The
but
classical
I mean,
foundation.
but your mean field result, that you get this passage, this transition from first order to second order.
That is of course model dependent.
Yeah. Do you expect this also to hold for those more challenging optimization problems, or?
I mean, it's not guaranteed at all. This is a very specific model where you can do calculations in the thermodynamic limit. You can do whatever you want, basically, with this kind of spherically symmetric systems, mean field spherical symmetric systems. But for spin glasses, I'm not sure that
but
you
for
can
spin
derive,
glasses, you can do replica things, etc.
Yeah, that's true. That's true.
I mean, it's a critical question, right? It's a crucial issue, because in the end you want to use this for hard optimization problems.
Yeah, you're right. But I mean, if you are able to derive the phase diagram of the model, then you have some insight that can guide you in designing this protocol. But if you don't, you can just treat it as a heuristic optimization strategy and see what happens.
Yeah, but you have no intuition or any evidence that this kind of transition from first order to second order will also occur in other harder cases.
As far as I know, this adiabatic reverse annealing protocol has never been applied to models other than this p-spin model. So as far as I know, there aren't any papers that speak about this, but it's of course a very interesting question.
Okay, thank you.
Any other questions for Gianluca? Okay, if not, let's thank Gianluca again for a very interesting presentation. Thank you.
Thank you all.
And look forward to seeing everyone at the next INQA seminar, which I guess is 7 days and nearly 8 hours from now. So see you all then. Thank you.
Bye. Thank you.
Bye.